Well, let's see here. I'll begin. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day, for the beautiful weather outside. I just ask you to bless this class, help us to just glorify you in what we do. Again, ask that the students would be able to understand and that they would be able to ask questions if they have them, Lord. In your name I pray. Amen. Amen. Okay, so if Top Hat's working, we'll see. My computer was refusing to connect here a minute ago. All right, 8529. All right. Now, so we're talking about graphing rational functions, right? Any questions before I dive into it? Yeah. I will collect the homework at some point in a few minutes. I'm just hedging my bets against people coming in late. But yes, that's a good question. I should collect the homework before we leave today, for sure. Yeah, you know what? Now's as good a time as any. If you wouldn't mind, turn your homework, pass your homework to the center aisle, and then I'll collect it. Yep.
So we're supposed to turn it in person?
Yeah, in person. So we don't understand. So yes, homework, I want you to turn the participation thing in person. Since there's a misunderstanding, apparently, I will take it Friday.
Okay.
All right?
Thank you. Thanks.
So I'd like it to be, yeah.
I did it like 1 month.
Yeah, you're okay. Yeah. So what I asked for was ideally to print out the page and then write the answers in. You don't have to show all the work. I just want the answers, like I said on the sheet, right? I say you just need to put the result from each example in the space that I provided. Yep. So it would be best for you, of course, if you actually work out all the long divisions, right? But I don't expect you to write that out and give it to me. Now, some of you didn't have a printer working for whatever reason, and so you have written it out by hand on a piece of paper and you want to hand that in. That is also fine. I'm going to collect those Friday, so I have them all Friday. I guess I could, if you want to give it to me now, I'll take it before you lose it. How about that? I know what happens here. Because if I wait till Friday, then somebody will be like, anybody else want me to take it now? I'll take it. Thank you. All right. We good? Okay. I prefer that you print it, yeah.
It's on Canvas.
It's on Canvas, yeah, yeah. But if you didn't print it, it's understandable. I get it. It's a sad commentary on your education as it stands that you have so many classes where you don't have any expectation whatsoever that you're turning in something on paper that you don't have access to a printer, right? It's like such an unusual request in the sphere of your courses right now, right? So that's kind of symptomatic of, I would say it's symptomatic of what's wrong with your education, that it's all electronic. But anyway, ask me, I'm a dinosaur, what can I tell you? Okay, so graphing. Rational functions. And I'm going to try to learn from my mistakes yesterday. I didn't really make mistakes per se, but I've got an idea about how to make this more understandable. All right, so we're given, excuse me, f of x equal to, let's say, n of x over d of x. All right, so I'm using n for numerator and d for denominator. All right, where n of x and d of x are polynomials. All right, these are polynomials. How do you graph y equals f of x in this case, all right? So here's how it goes. Step number one, excuse me, completely factor. You completely factor n of x and d of x, all right? And then that's step number one, all right? Step number two. List zeros of n of x. List the zeros of d of x. In other words, you're looking for places where either the numerator is 0 or the denominator is 0, all right? Make a list of them, okay? So like maybe the numerator one has, I don't know. Well, let me not even make any notation for that. That's what we're going to do. We're going to list them, okay? I have a temptation to write out like symbolically what I'm talking about here, but let's not do that. It's distracting for me, for you guys. So you make a list of the zeros of the numerator, make a list of the zeros of the denominator. 3, you make a number line where all the zeros are marked. Okay, so I'm talking about all the zeros from step 3. All right? And you add pluses and minuses as appropriate. Okay? Great. Step 4. All right, step 4. What we want to do is if the degree of the numerator is less than the degree of the denominator, then y equals to 0 is your horizontal asymptote. For the graph, okay? On the other hand, if the degree of the numerator is greater than or equal to the degree of the denominator, then long division is needed. And what you'll find from the long division, is that f of x will be equal to, let's say, p of x plus the remainder of the long division divided by the denominator. All right? And in this case, y is approximately equal to p of x for x going to plus or minus infinity. So what I'm saying is if the numerator has a larger degree or equal degree to the denominator, the way the rational function is going to behave very far out is totally governed by the polynomial piece. Okay, sometimes that polynomial could be a constant, all right? That we have, if it's a constant, you still got a horizontal asymptote. If the polynomial is like a linear function of x, those are called oblique asymptotes. You could have this polynomial be quadratic, then you'd like asymptotically go to like a parabola. If p of x is a cubic, your large scale behavior looks like a cubic, and so forth. All right. Oftentimes, guys, the lion's share of the examples we'll do in step 4, we'll just find ourselves in the first case. In the case that the degree of the numerator is smaller than the degree of the denominator, so great, easy. And then step 5 is to graph. Let me add a little bit of nuance here to step number 5. Okay, so given a 0 of 0 for n of x or d of x, all right? Then here's how this works out. Let's say a 0c. Then if x minus c appears most in the numerator, then, well, I'm sorry, I'm still making it too complicated. Let me put the dumbest case to start with, and then I'll add nuance, okay? This is usually what happens. The simplest case is when there's no interaction. Given a 0c for n of x or d of x. So like, let's see here, part 1. If x minus c is only a factor for the numerator, then c comma 0 is x-intercept for graph. All right, so if the factor appears only in the numerator, great, it's an x-intercept. Game over. Okay? 2. If your factor x minus c is only factor for the denominator, then x equals to c is a vertical asymptote. All right? Very simple. If it only appears in the denominator and makes the expression blow up, you get a vertical asymptote. No trouble. Here's where it gets a little bit subtle, is when you have the factor both in the numerator and the denominator. See, that's the tricky case. So if x minus c is in both n of x and d of x, if it's in both the numerator and the denominator, there's a few different things that can happen. All right? So then you have like when the order of x minus c is same for both n of x and d of x, it's a hole in the graph. It's a hole in the graph, and you can find it. You can find where the hole in the graph is from what's called the reduced function. All right. When the order of x minus c is larger in the numerator than c comma 0 is whole in graph. Now, technically speaking, you could think of that as being a subcase of the top case there, but fine. And then finally, if you have x minus c has larger order in the numerator, then x equals to c is vertical asymptote. All right? And then you put all this together and you can graph. I know it's a bit of a mess. I'm sorry I didn't have a handout of this for you guys. I really wanted to. And I'm teaching this course online right now to a student at my previous school where I was at. And that course is just kicking my butt. Like, it takes forever for me to write notes for that thing. So I didn't get to write new. So I'd like to make this into a handout, yeah? But I don't have it yet. I should have it before too long, though, okay? It is my intention to, like, clean this up and give you a handout on it. Let's put it into practice, though, yeah? So example 1, let me try to like just dig into this part 3 and show you what I'm actually saying here, okay? So y equals to f of x. Let's suppose you've got, you know, x plus 1 times x, x minus 2 cubed, and then x minus 3 squared, all right? And that divided here by x plus 1, and then x, let's see here, x minus 2, let's see, I'm trying to think here. I want the same, I want larger, there, like that. And then x minus 3 to the, oh, I don't know, 4th power, okay? I may regret this, but here's the example. So in this case, this is the n of x is the top, right? My numerator, here's the denominator, right? Zeros. What are the zeros? Minus 1, 2, and 3. What are the zeros for this? Again, minus 1, 2, and 3, right? So and we can make a number line. Let's do that. So I've got to put a minus 1 in here. I got 0, got, let's see here, 0, 1. I'm trying to keep my scale. All right, so that's 0, 1, 2, 3. All right. So there's my number line. Those are the critical numbers for this function, right? A critical number, like we talked about before. Remember, we studied these kinds of things at the start of the course. Remember, we did rational inequalities. We made a number line. We identified all the critical numbers. We put pluses and minuses. This is the same exact thing as that. The difference is now we're going to the next step to graph the thing, all right? But the starting point here really is the same as what we did before. Although we didn't do a lot of these, I guess. But so what do you got here? Plug in a point to the right of 3, like for example 4. What happens when you plug 4 into this? Everything's positive, right? Plus, 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 plus. So we got pluses up in here. Now at 3, the question is, do we flip sign or do we maintain? Well, how many x minus 3 factors are there? There's 2 up here, there's 4 down here, there's a net of 6 of them. That means we're gonna bounce in the sense that we're gonna maintain sign going from 3 to the region between.
Divide, right? Like you're just adding the net.
Adding the net, right? The question is overall how many factors. So we just add the orders from both. You're just counting the number of factors. It doesn't matter whether it's in the numerator or the denominator for this part of it. So like 2. I've got this x minus 2 cubed, and I've got this, oh goodness gracious, this is all positive, isn't it? Son of a gun. Can I change that just a little bit? I want to make this more interesting. Is it okay, guys? I'm going to change this 3 right here to a 4, okay, if you don't mind. And the reason I'm going to do that is now, how many x minus 2 factors do I have with that change? And now I've got 5. I've got 5 x minus 2 factors, so that means I flip signs here. So the sign flip theorem still works. If you've got an odd number of factors, you flip the sign. If you have an even number, you don't. Now x plus 1, above and below both, I have 2 of them, so it keeps negative, all right? Oh man. All right, guys, you'll forgive me, but I need to do something for the sake of, like, this as it stands is ugly. This is an ugly problem because upstairs I've got 2 plus 4 is 6 plus 1 is 7. I've got order 7 for my numerator, right? What's my denominator order right now? 6. What does that mean? To do the graphing properly, I have to do the long division. To do the long division, I would have to multiply this out. We want no part of multiplying that out. That is a bad place. We do not want to go there. None of us are paid enough money to do that. All right? Is anyone paying you to take this class? No. No, okay. Cost you money? Yeah, okay. Pound of flesh. Okay, so to fix this and not change my sign chart, it's pretty simple. I'm just going to change this 4 here to like a 6. I think if I do that, then we're good. So sorry, I'll get with it eventually here. 6 plus 1 is 7. Now we have order 8 in the denominator. We have order 7 in the numerator. That means we're in the easy case of step 4 over here, right? We get y equals 0 as our horizontal asymptote. Okay, good. That's what I wanted for this example. All right. Let's see. Have I done everything? I factored it. I made my sign chart. I listed my zeros. I am now to the graphing step. All right, so let's do it. So where's the y-axis is like right here, right? Now, oh, well, that's going to sting a little bit. So let's see here. Let me start with the 2. If we look at 2, right? Oh, fine. If I start at minus 1, what's going on there? Minus 1. So c equals to minus 1 is hole in graph. Because we have x plus 1 upstairs, we have x plus 1 downstairs, right? So they have the same degree, so that means it's a hole in the graph. I said you can figure out where the hole is by looking at the reduced function. What's the reduced function here? The reduced function is what happens when you cancel out the x plus 1s and leave everything else. So like f reduced here. Whoa. Impressive. Let's see here. X minus 2. That sneeze is nothing to sneeze at. Let's see here. X minus 2 to the 4th power. X minus 3 squared over x minus 2. This is like every morning at the breakfast table, my son Daniel sneezes, and like there's going to come a point where he sneezes in his mother's face, and like she knows it's coming, because every morning he has sneezes. So like she's always just like sneeze to the side, sneeze in your shirt, like just not like this forward, because it's just a matter of time, right? So there's just this ongoing battle. But anyway, so that's the reduced function. So all I did here was take the formula and cancel out the x plus 1s. This is what the formula is. This is equal to f of x, right? For x not equal to minus 1. That's all. So to figure out where the hole is, I plug minus 1 into the reduced function. And what's that give me? Oh, see, it's horrible.
Do you do that every time, or can you just sit and degrees are equal? Or like, are you just explaining?
I'm explaining how to find where the hole is. You do this, but so the thing is I got to plug minus 1 into this.
But like, you necessarily wouldn't have to do it, is that what you're saying?
I'm saying that if you want to put the coordinates on the hole, then you got to do this.
Okay.
So if I say label any holes in the graph explicitly, you got to do this. But anyway, here it is, minus 3 to the 4th power. Oh, goodness gracious. Minus 4 to the 3rd squared divided by minus 3 divided by minus 4 to the 6th power. So what is that? I mean, that does simplify, doesn't it? We've got minus 3 to the 3rd power divided by minus 4 to the squared. Okay, it's not that bad. It's just minus 27 over 16. Okay, fine. It was scarier when I started. It's not that bad, actually. So the hole is at minus 1 comma minus 27 over 16. That's where your hole's at for the graph. Now, so that makes sense that it's negative because the graph here is going to be negative. So just, I mean, this is a really, really weird way to start the graph, but it's got a hole about right here. Okay? There's minus 1. There's a hole there. Great. Now, it stays negative, and it goes asymptotically to y equal to 0. So something like that is where we're starting. What's, and then we get to x equals to 2. What's the deal with x equal to minus 2, rather? C equals to minus 2. What's the deal there? You have x minus 2 to the 4th over x minus 2, right? That's the part of the f of x which is relevant to the 2. There's a 4 upstairs, there's a 1 downstairs. This means that we're in, like, we've got larger, right? So this means c comma 0 is a hole in the graph. So here 2, 0 is another hole. It's right here. Something like that. So notice that the graph is negative from there to there. Okay, then what happens at 3? Right? There you've got what? You've got x minus 3 squared over x minus 3 to the 6th. Okay? So that means that the denominator one wins. When the denominator wins, you've got a vertical asymptote is what that means. So we've got a vertical asymptote at 3, which looks like this. Okay? And so what's going on here is this goes up like that. It's positive, right? And then apparently it's like a volcano because it stays positive on the other side. And then it's going to y equals to 0. That's our eventual, like, long-term behavior here. And so there you go. That's the graph. And again, this we had to work a little bit, but that was minus 1, minus 27 over 16 is the coordinates for that hole in the graph. The coordinates for this hole in the graph was just 2, 0. So it's like it's way easier to find the hole in the graph if you have the numerator having a larger degree than the denominator, because then it's just on the x-axis. You don't have to think about, you don't really have to think about the reduced function necessarily. The vertical asymptote, why do I have vertical asymptote?
Yeah, why is that the vertical asymptote?
Because that's, so we x equals to 3. So this function, right, there's 3 points that are not in the domain. You don't have minus 1, you don't have 2, you don't have minus 3, right? I mean, you don't have minus 1, you don't have 2, you don't have 3. These are the 3 points that are troubling. So when you have a point that's not in the domain for a rational function, it's either a hole in the graph or it's a vertical asymptote. The hole in the graph, though, can either appear on the x-axis or off it. So if it's off the x-axis, we do this thing. If it's on the x-axis, though, here we have larger degree, so that puts the 2, 0 there. This 3 one, the reason that's a vertical asymptote is because we have a larger degree in the denominator. That's the difference between this one and the other ones. Numerator wins. It's a hole in the graph at the on the x-axis. If the denominator wins, it's a vertical asymptote. And if they're
Did you write the last point wrongly? It says if larger order, and I think it's fine.
oh, what have I done?
Would it be if it's a larger order than dx, then it's the vertical asymptote? The last point you said.
Oh, yeah, that's supposed to be D. Thank you. I think I said D and I wrote N. I'm a dummy. Thank you. Excellent. Bonus point, email me. Every so often someone makes a correction in class that has saved other people points on their test. Those are with bonus points. All right, so example 2. All right, so let's work a less complicated example, all right? Sorry, that one was kind of a beast. But that example is obsessed with the tricky part of this problem space, yeah? That's the tricky part. Okay, so let's work something a little bit less onerous. let's graph y equals to f of x equals to x squared minus 4 over, let's say, x squared plus 3x plus 2. Okay, so how does this, so first order of business, factor, right? So we got a factor. We've got x plus 2 times x minus 2 divided by x. Hey, check that out. There's an x plus 2 down there too, right? So this one is, it's still got part of the badness, right? Because there's a common factor of x plus 2 shared in the numerator and the denominator, right? So that makes us think a little bit, but they're equal, right? They're the same order, right? So that means that that's going to correspond to a hole in the graph. So our zeros, we've got what? Yeah, minus 2, minus 1, and also the positive 2, right? Make your number line. So number line, I got my minus 2, my minus 1, my 2, all right? So let's figure it out. What is this? Like all of my examples, apparently, it starts out positive over here. Eventually, I'll remember to make one that starts out negative. Sorry, I have not been, making the examples start out negative. It's just a force of habit. I like it to start out like, I don't know. It's just, I could mess it up by doing like 4 minus, if I did like 4 minus x squared, that would put minuses over here, you know? It's not hard to make it happen. Then what? So look at 2. This is coming from what? The 2 here comes from the x minus 2 factor. How many x minus 2 factors do you have in this?
1.
Just 1. So we flip the sign from plus to minus. All right? Then I'm at minus 1. That comes from what? That comes from an x plus 1 factor. How many x plus 1 factors do I have here? Just 1. Again, I flip the sign. Now, minus 2 is coming from x plus 2. You got 1 up here, and you got 1 down there, right? There are 2 of them, so you stay on plus. Stay plus. There we go. We've made our sign chart. All right? Yep.
So if it's like odd, is that when it like changes?
If the net number of factors you have is odd, it changes sign, right? So in my horrible example 1, we had 5. We had 5x minus 2 factors here. That's why it flipped at 2. Because there was 4 upstairs and there was 1 downstairs. I mean, okay, so at this point, I think about what's my game plan here for graphing. I do need to I need to pay attention to step 4, right? Step 4. Oh no, look at that. It looks like we have to pay attention to step 4 here, don't we? I hope you've top hatted because I'm about to erase that. Haha. Okay, so we got to do the long division here, right? Because you notice that the degree of the numerator is equal to the degree of the denominator. In fact, technically speaking, you don't really need to do the long division here. I can tell you what the horizontal asymptote is going to be. It's going to be 1. All right, but let me go through it. So I'm dividing x squared plus 3x plus 2 into this. So I put a 1 here to get that. Then I subtract. At this point, we're done. It's because we've got minus 3x minus 6. And that's your remainder. So what this calculation here means is that f of x is actually equal to 1 minus 3x plus 6. I pulled the minus out, okay? Divided by x squared plus 3x plus 2. So like conceptually what's going on here is for the graph, if we're really far away from the origin, if where x is really, really large, positive or negative, if it has large magnitude, this piece right here, it's small. It's very small for large x in either direction. So this piece goes to 0, and we're just left with 1. So the graph is going to tend to the number 1 eventually. That makes y equals 1 a horizontal asymptote. So I should try to make that a feature of my graph, all right? So y equals 1 is a horizontal asymptote. Let me put that in there. Okay, great. So now we're to the graphing step. Let's take stock of what's going on here. Minus 2. What can you say about minus 2? I'll put more work over here. Like if we look at c equals to minus 2, it's a hole in the graph, right? Because we had x plus 2 and x plus 2, same power, top and bottom, right? In this case, the reduced function is easier than the last one, because here the reduced function, you just cancel the x plus 2's. The reduced function here is x minus 2 over x plus 1. Okay, so where's the hole? So f reduced of minus 2 is minus 2 over minus 2 plus 1, also known as minus 4 over minus 1, also known as 4. So the hole in the graph is where? Negative 2, 4. Okay, so we've got that to look forward to. Let's see here, minus 2, 4. So that's kind of, well, let me use, I've been graphing in red, so I'll just try to stick with that. I may have made a poor life choice in making that 1. Oh well. I made my, there we go. So our hole is roughly speaking there. You know, whatever. How about minus 1? What's that? Minus 1 is a vertical asymptote, right, because it only appears in the denominator, so no problem. So minus 1, because we have x plus 1 in the denominator, that gives us a vertical asymptote at x equals minus 1. How about 2? 2, finally, a sort of normal point. 2 is coming from the x minus 2 upstairs. That is a 0. So we have an x-intercept at 2. So that would be here. Okay? So I have a point on the graph. I've got a hole in the graph. I know it's drifting to 1 eventually, and I've got my sign chart. So here's what I'm going to do. It's doing something like this, basically. All right, so like I said, I made a poor choice in terms of the vertical scaling. Anyway, it's like this. All right, and then you get to minus 1. What happens? It flips down here, right? It's an asymptote. It's got to go down like that. Where does it hit 0? I mean, you could figure that point out, right? What's the y-intercept? I think it would be nice to add a y-intercept, don't you? Y-intercept, where is it? F of 0. What is f of 0? Minus 4 over 2, also known as minus 2. So the y-intercept is actually at minus 2, which is right about here. What's that? How did I figure out the y? The y-intercept, when I plug in 0 into the formula, I get minus 4 over 2. When you plug 0 into x, it just goes away. You're looking at the other thing? Yeah, that's cool. So there's another point in the graph. So that gives me some sense of scale. So it's something like this, you know. And then what happens past here is it just kind of asymptotically goes up to like that. So, I mean, my graph's a little lumpy, but that's roughly speaking what this thing looks like. All right? it might be interesting to simplify this. Here's a bonus comment. Can you simplify this? Pull the 3 out, right? See what happens here? See this? What is this? This is the reciprocal graph, right? It's the reciprocal graph. What have we done to it? We've taken the reciprocal graph, we've shifted it 1 to the left, right? We've moved it up 1. Well, I mean, fine. We take the reciprocal graph, we stretch it out by 3, whatever that means, right? Shift it 1 to the left, and then shift it up 1. That's what this is right here. This is the reciprocal graph stretched out vertically, flipped over. I'm forgetting the minus here. Flipped over, right? Shifted 1 to the left, shifted up 1. So you could see this from the transformations of graph stuff we did about a week ago. Maybe more than that. A little over a week ago, I think. And then you take that and you punch a hole in it. That's another way you could graph this. But I think the way we did it with the algorithm is easier than that. Like, you can do a lot of things with transformations, but is it the best way? I don't know. I mean, transformations, yeah. If you saw to do this with transformations, I'd be delighted, sure. As long as we can agree on the graph at the end, like how you do it, kind of your business, but you know, no graphing calculators obviously, but yep.
What point's on the x-axis?
Oh, thank you. This point right here is the 2. Yeah, and this, for what it's worth, it's also -2. As you can see, my scale is not quite. It's a little bit. This distance and that distance are a little. I mean, I'm a little crooked. All right, enough about holes in the graph. I already know if I have a question on my exam and I put a hole in the graph, I know half of you are going to get it wrong. It's like written in stone. So there will be other problems where there are not holes in the graph. Let's do some examples like that. I know the whole thing is a little bit tricky. Here's one that's a little bit less tricky. If we had f of x equal to x minus 2 squared over x plus 3 times x minus 5 squared. All right? So I already factored it for us. Let's make the sign chart. Our zeros are what? We've got one at -3. And then, let's see here, 0. We've got one at 2. And one at, yeah, over here at 5. Not to scale. I'm just kind of guesstimating it. So we have pluses over here. All right. Then what? I think I never. I am my own worst cameraman. What's that?
Can you use 0 as a test point?
Sure, but you could. That would be in here, right? What would you get? Positive. Yep. Positive you could do there? Sure, let's check on that. So when we get to 5, what happens? We bounce, right? I mean, well, we stay positive. When we get to 2, it's a square, so we stay positive, right? When we get to -3, though, there's just one of those, so we flip signs. All right? Now we can graph. All right. Thankfully, there's no hole in the graph here, right? Because there's no, there's the 2, the -3, the 5. The -3 and the 5, those are what? Those are in the denominator, right? So those give us vertical asymptotes. We have a vertical asymptote at -3. And we have a vertical asymptote at 5. We also have a 0 at 2. And just like with the polynomials, what happens when you have a square like that? You know what you do? You bounce. So what this is going to look like is just this. We bounce. It's a volcano. How do I know that my horizontal asymptote is y equal to 0? How did I know that? How do I know that I'm not drifting to like 1 or something long term? I've got a quadratic upstairs, and I've got order 3. I've got a quadratic over a cubic. I've got a 2 over a 3. Denominator wins, horizontal asymptotes y equals 0. In other words, we don't have to do the long division thing to figure out the asymptotic behavior here. This is the nice case. So right here, this is the sweet spot for like the quiz and the test, problems like this, right? Definitely there's going to be a problem kind of like this. So you make sure you can understand what we did there. Do you see the difference? There's a lot going on here. The bounce, why is there bounce? Because we had x minus 2 squared, right? If that, yeah?
Oh, I was just saying, if there was like a negative, and then it was a -2 afterwards, would you move your vertex down then?
-2 afterwards?
Like if it was x minus 2 squared minus 2, I'm just asking like in terms of
-2? Oh, like this? Oh, if this was -2 altogether?
No, if your numerator had -2 on the top.
Just a
That's
-2
what
up.
you decided-
Oh, just a -2 like that?
Yeah. Well, because you had just made 2 your.
Oh, if I had,
So just asking
if I had that.
would that change the problem?
It would change it a lot. See, because then this would be x minus 2 plus 1, x minus 2 plus minus 1.
Okay, so never mind.
And-
I'm just curious on why you made your vertex 2, 0.
This is 2, 0 because there is a x minus 2 squared up here. So that means the function 0 at that point.
Okay.
And it bounces because it got square. So
Oh, okay.
yeah. Listen, we'll do more. We're not done.
I was just curious.
Yeah. This takes a while. If you look at the syllabus, we're a few days ahead. So like we have time to let this marinate. Yeah.
What?